Greetings viewers, Eric the Car Guy here with Kevin Frische of Calvinator Engines. And we're balancing stuff. Well, Kevin's balancing stuff and I am observing, and you can observe too. Right now we're balancing connecting rods. And what's the reason we want to do this?
So the engine runs smoother, on RPM quicker, reduce the vibrations in the motor from the, there's enough going on inside just the natural combustion process, let alone having on a V-style engine especially, all the forces working against the crankshaft. So we try to weight match everything. Plus or minus 1 gram is what I typically go off of, and we're right there. The nice thing about today's manufacturing processes is these things are really close right out of the box as far as all your pistons weighing the same, all the rods weighing the same. This isn't too bad when you figure that there's 28 grams in an ounce, and we have our plus or minus 1 gram.
So you're laying them in order of what weighs more and what weighs less?
Yeah.
So we've just got one that's a little bit oddball?
Yeah, 414.
So we just add a little bit to that?
No. Unfortunately, we need to take the heavy ones and make them weigh 414, 415.
Ooh.
Well, I could, if I'm going to go with my plus or minus 1 gram scenario, I'm looking at 3 rods, right?
Right.
Okay. And we split these. We weigh these, the big ends, and then we weigh the small ends. And you balance the big ends first. Reason why I divided big end and small end, the big end is on the crankshaft, and that's rotating. The small end being in the cylinder, that's reciprocating. So we use the mathematical formula. I use a different percentage for the rotating and the reciprocating weights. So we can get into that here later.
In essence, if these are all balanced and the rotating assembly of the engine is balanced, it's going to run smoother, as you said, rev quicker.
Yes.
And it'll be less susceptible to harmonic forces or whatever inside of there. So that's kind of the whole point. If it's all balanced and working correctly, it's all working together nicely.
Yes.
So the only thing you can do is remove material. You can't add material.
Don't really want to weld in a rod.
No.
So.
No. All right. Well,
we'll go figure out how best to do this and come back and reweigh some.
Engine balancing. It's fun, kids. You cannot try this at home.
I want to remove them burrs. I don't like burrs. Turn into metal slivers, fly around, get in your bearing, and then you got problems.
We don't want that.
No.
But in essence, you just sort of do that by feel and say, okay, 1, 2 second per gram kind of thing.
If I made them too light, we now need to make the rest of the rods weigh what this is.
So I guess the 2 second gram count is
Pretty close.
pretty darn close.
Yeah. There's shops that'll get them within 1/10 of a gram. You can spend time and do that, but there's the other factor is you don't know how much oil is clinging to the crankshaft and your components when it's spinning inside the engine anyhow, and oil has weight too. So we could spend hours getting it even closer than this, but for what real reason?
Diminishing returns after a certain point. So when you put it on like this, you're measuring the small end.
Yep, we're measuring the small end now. Well, I'm down to basically 3 again. I could hit these and get them closer too, but I'll start with these. We'll start with the heaviest one, try to alleviate any mistakes. Here's 76. That was the heavy one. That one didn't really change. Maybe this one did. 74. All right, I'll do that again. I'm getting closer. 173, 173.
It's so amazing how this all comes down to little marks
173.
with a marker. So much of
right.
machining is marker.
That's right. There, that looks a lot better. I think we'll leave that alone. And then we need to weigh our pistons, rings, pins, locks,
Wow,
bearings.
that's a lot of weighing. If you want to do it right, it's a lot of weighing.
Yeah, just weighing the individual components. The piston 416, the pin is a 130. The locks, it uses 4 per piston. Should be 4 grams, and it is.
Because these are not Preston pins, they're using the spiral locks. And you're weighing everything individually as opposed to just putting it all on there and weighing it as an assembly?
That way, if we ever need to replace one component, I know what that, say you heard a piston, I can call and say I need a this part number piston, 416 grams, so we don't have to, we get one with the matched weight, so it's still basically a balanced assembly. And I forgot a rod bearing. Dadgummit.
Hey, if you need to, I found your bearings.
So now we do the math. You gotta add it up.
So you only have to weigh one set of rings, one set of bearings.
Yes, and when I do the weights, I'm going to use 100% of the rotating weight and 50% of reciprocating weight, what goes up and down in the cylinder. So, but we got to figure that we have 2 assemblies on each crank pin. So to make up my bob weight, and this is the bob weight, make that.
Oh, so this is all being done in preparation for balancing the crankshaft.
Then the 4 of these will go on the crank, and then we'll spin the crank and see how far out it is, and drill, hopefully remove or add material wherever we need to make it balanced.
That's exciting. We'll be back, kids. All right, Kevin. Last we left you, you were going to go through and do some math to try to figure out how much 2 rods and pistons would be on a crank journal so that you could make this over here on the scale. Can you talk a little bit about what you're doing?
Okay, this is what we call the bob weight. This is going to attach to the crankshaft, simulating the weight of 2 rods and pistons on that crankshaft pin, which is typical for your V-style V8 application. So, and we come up with 1698 grams. So we just add 2 more washers to this, and I got my 1698. And that's simulating 2 rods and pistons assemblies on 1 crank pin. And then we'll attach that to the crankshaft. I already have the other 3 on.
So the reason why we would do this to begin with is we don't want to put the pistons and rods and everything together, put them on this balance thing and have them just flinging around.
I'd probably hurt myself.
So this is meant to simulate that weight on the crank so that we can get an accurate balance by the time all is said and done.
Absolutely.
Okay, so that's why we're doing what we're doing.
Now, this is being an externally balanced application. We need to have the harmonic balancer and the flywheel or flex plate mounted to the crankshaft, so it is exactly like it will be when it is installed in the car. So that's why you call it the balancing the rotating assembly.
So if you went to your machine shop and you wanted your rotating assembly balanced, this is the process that they would go through in order to do that.
Correct.
And you've already got all the other weights. This was the last one in the process. And we have the new flywheel. We also have the new harmonic balancer all together because it's balanced as an assembly. Now, one more time, can you go over why I'm not using my old flywheel and I'm going with this other one?
Okay. Yes, your original assembly was from the 1980 and above. So that's what they call the 50-ounce assembly. In other words, the weight, we got a weight here on the front, it would have been a 50 ounce, and then we had the weight back here on the flywheel, and that would have been 50 ounce. So a lot of your aftermarket crankshafts are balanced to, or manufactured to use a 28 ounce weight. So that's a 28 ounce weight. And then I changed out your harmonic balancer on the front anyhow, which is also a good idea because the rubber in here will deteriorate.
Right.
So if you're doing a performance build, replace it with an aftermarket harmonic balancer. Flywheel and the harmonic balancer, both SFI approved for safety purposes. In other words, this outer ring is going to be it's not a cast steel or cast iron like your factory one. I've seen these explode at high RPM, so that's a good safety thing to do.
And I was just going to ask you about that because compared to my other weight that had the rubber on the inside that was actually sort of leaching out.
Yes.
It seemed like something like that, or I've heard of at high RPM that can come apart, but I noticed this one, everything seemed all encased.
Yes.
So it didn't seem like it was built so that it even could do that.
Right. And then I like the SFI approved flywheel on the back. That way it doesn't cut your feet off when it explodes.
Well, that's a really great thing. Thanks for looking out for me, man. Especially my feet. I need those to walk. That being said, also like a scatter shield or something would also help, just in case. Or,
absolutely.
As an extra measure.
Steel bell housing, yes.
Yeah, just put something around the outside of that to help prevent that from happening.
So now I got to set the RPM in the balancer.
Okay. Cool. And so that's what's happening as the engine's running.
A little more lubricant.
It's also worth mentioning, we had talked about earlier that the crankshaft had not been balanced.
Right.
When you purchase an aftermarket crankshaft like this,
yes. There is no holes in here to indicate that any balancing has happened previously, so you need to balance the assembly. And some manufacturers, you can order them as balanced assemblies.
Okay. So if you're shopping for a lower assembly, a crankshaft or something like this, and you don't want to go through this process, you have to make sure that it's a balanced assembly before you purchase it. Other than that, you're going to get something like this, which is in essence a blank, so to speak, that you have to go in and balance like this with all of your rotating parts intact. Now, say for instance this was an automatic transmission and we didn't have a flywheel, we had a flex plate, would we still need to have our flex plate there?
Yes, because the flex plate will have a weight on it too. Since this is an externally balanced engine, what we need by internally and externally balanced is the job of the counterweights. Let's start back here. The job of the counterweights is to counterbalance or counteract the weight of the rods and pistons. Well, the 302 Ford is a smaller block, 8-inch, 200 deck height. The crankcase down inside is small, so we can't make our counterweights huge because they just won't swing in the bottom of the engine. So we come outside the engine or external to the engine and we add some weight, and that allows us to balance the crankshaft to the weight of the rods and pistons.
So no room inside, but there is room outside, so we balance the crankshaft on the outside. Right. Which is just as good?
Well, you can order internally balanced crankshafts. They're going to be your higher priced ones. One the other week was about $2,800. So,
do you think it's also worth mentioning this is a forged crankshaft over a cast crankshaft, which is also more expensive?
Yes, this is a 4340 forging.
So those are also more expensive, but stronger because of the manufacturing process going through from forging to cast. The way I tell the difference is something forged doesn't have any seams on the weights or anything like that. A cast crank will have seams that you'll see going along the crank because they cast it together like a sandwich.
A cast crank will have a very narrow parting line. The forged crank, this is a wider parting line. So that's a very easy way to tell. It's something to note here is the counterweight, as I was talking earlier about the weight not being substantially physically big enough to offset the weight of the rods and pistons. This weight added to the flywheel is right in line with the counterweight, and the same way on the front. The harmonic balancer, the external weight, is right in line with the counterweight on the crankshaft. The bolt pattern on the flywheel is offset, so the flywheel will only go on one way because we need to make sure that weight is lined up with the counterweights. Some applications will use a dowel pin. Ford chooses to use an offset bolt pattern.
So you can only bolt it on one way?
Yes.
And as far as the balancer on the front, that's keyed?
Yes.
So that only goes on one way. So Kevin, why set an RPM of 500, which I noticed is what you had when you did this initially when you were testing?
That's, for the easy answer is that's what the manufacturer recommends. I have spun some of them higher. I've done some inline engines that some of the import guys like to turn higher RPMs. So I'll spin them 750 RPMs. And it does change a little bit.
Okay.
So, but this application, we're doing 6,500 RPM, thereabouts. You know, that's all your hydraulic roller cam really is good to, theoretically.
So that's not 500 RPM, that's 5,000? That didn't seem like it was going that fast.
No, it's not. It was 500 RPM.
It's 500 RPMs.
But just the natural resonance of some materials, as we was talking about earlier, when you balance a tire, you know, it may vibrate at 60,
right,
and then it won't get to 120.
Right. So, and that's what we were talking about off camera a little bit, is that metals and materials have a certain resonance. So when they reach a certain RPM, they have a vibration, a certain frequency that they're affected by. And maybe that's why they say 500 or whatever on these.
Yes.
Or what have you. It just depends on the type of metal and how it's put together. And we're trying to balance something, so we're trying to basically minimize those vibrations so that we have a clean, smooth running engine.
And then we've spun the crankshaft, and when the numbers we end up with is it's telling me we need 194 grams out of the front of the engine, 223 out of the back of the crank at 14 degrees. So if I rotate the crankshaft, that little dude says 14, so 194 grams right here. And then on the back side at 41, we have 223 right here. So obviously I can't do that in one hole, so I will split the difference. We'll do it in 2 holes.
I have seen them, and as far as the other holes. So if I'm reading this correctly, this is the amount that needs to be taken out of the front, because we're not
Correct.
adding weight, we're removing
Yes.
weight. So this is the amount of weight that needs to be taken out of the front. This is the angle at which that material needs to be removed, which in this case is 14 degrees.
Correct.
And this is an indicator of what degree you're at. So you just went to 14 there.
Yep.
This is the rear, which is minus 223, which you talked that it was a little bit much. You have to split it up, and that's at 41 degrees. So just like when balancing a tire, you spin that one up to 41.
There.
And it's all lined up. So when that's at that placement, you can just remove material with the drill press.
Correct. And we did double check. We took this weight off just to see how much that affected things, and it totally flipped everything to the other side. So the weight it's doing its job. And I could have trimmed the weight. Doing that in my mind is just wrong, because what if Eric later on decides, you know, I'm old now and I don't want to shift, so I'm going to go automatic. So if you switch to a 28-ounce flex plate, this thing is still balanced.
It's balanced.
So I'm not going to cheat. It's not,
Yeah, so getting rid of that flywheel means that the balance is going to be all off in the crank assembly.
If I would have made my correction on the flywheel,
Right.
yes. So we're going to keep it on the crank so you can do whatever you need later on.
Cool.
Keep it flexible.
I appreciate that. So in case I get old and decide I don't want to shift.
That is, I just marked the 41.
That's the high-tech tool you have. I'm telling you,
That's
machining.
right.
What I've learned today, the takeaway has been machining is all about using your markers.
It is. We would live and die by the Sharpie.
Machining is all about your Sharpie. Your machine work is only as good as your Sharpie.
Since I'm going to have to make
Okay.
2 holes, I'm going to divide the distance equally from my 14 degrees and 41 degrees.
So you put a little bit of machinist blue, is that what that's called?
Yeah.
On the crank weight, and then you're remarking.
Yeah.
Because he doesn't want to drill a hole like halfway to China through this thing. He wants to split it up over 2 holes.
The closer you get to the center line of the crank, the less effect the material removal has.
Mm-hmm.
So 2 shallower holes would be better than 1 really deep hole, because I'm getting closer to the center line. And that's why we pick on the end counterweights to start with, because the closer I get to the center, the less effect the same amount of material removal has. 1 inch 100. So that'd be 550, right? Half of that. The way they manufactured the crank with this optical illusion where the center line is when I'm trying to look at it. And if I get off, next thing you know, I'm walking out the side of the crank with the drill bit, and that's not good for anybody.
So hence the reason that's why you're using the machinist blue.
Yeah.
So you can make that scribe there.
Yeah.
That much easier.
There we go.
So between the mark you made going across, then that you've got a crosshair.
Yeah.
Nice. And so you know basically how big a hole you're going to make, and you can just go on either side of that line, and you nailed it. I take it you've done this a couple of times.
Once or twice. So I wonder how many degrees I want to go.
So now you're at 45.
All right, so I'm gonna go 4 degrees on either side.
Okay, so 4 degrees on either side of what you were doing. So
Yeah.
So you're going by the
This would
measure
be
twice and
equal.
cut once?
Yeah. It's kind of a bummer to have to put that metal back.
Indeed.
As I drill, then I got to make sure I'm far enough away, otherwise the holes intersect and you didn't get anywhere. I want it close enough. They're close together, but I don't want to intersect too soon. So I think I'm going to go there and there.
How deep would you drill normally?
Well, we got to do the math yet, but since this is only 1 inch 100 wide, I'm not going to use a 1 inch drill bit, so I'm going to do probably a 7/8 drill bit.
Okay.
And we'll see where we end up. We'll do the math on how much the diameter and the depth, how many grams ought to remove. It's one of them deals where you want to sneak up on it. Because like I said, it's always a bummer to have to put that material back.
Explain this chart to me a little bit.
This is just material, how much the weight of the material from the holes has changed. And this is particular ones in steel, that's fine. We're working with 4340 steel. The counterweight's 1 inch 50 or 1 inch 100 wide. I'm gonna back up and we'll go to 7/8 drill bit, which is 875. So a 1 inch deep hole will get 77.2 grams. Plus with the point of the drill, an additional 6.7 grams. We're gonna have to probably go a little deeper, and the back may end up, well, we'll just see how it is. It might end up at 3 holes.
Okay.
I just don't want the 3 holes to be gargantuan deep.
I get it. And that keeps the shavings from getting on the part that you're spinning?
Right.
Which is important.
Anytime you got to drill a large hole, a pilot drill or a smaller hole first always makes life easier. This is the part that takes time.
Like a fine wine, machining takes time.
Yeah.
Kind of scary drilling into a brand new crankshaft, isn't it?
I'm over that now, but yeah, years ago, and oh man, talk about nervous.
Now, will these holes like affect the oiling, or, I mean, do they have any adverse effects or things that you have to watch out for? You expressed some trepidation about drilling too deep.
Oh, that's because we're getting to the center line of the crankshaft, and we're really not having that much of effect on balance. You know, I'm making it deeper and I'm removing material, but it's not affecting the balance of it as much. So I want to stay out towards the outer edges of the counterweight. If we had a really stout metal lathe, you could turn the diameter of the counterweights down. to match.
Same as you did the connecting rods.
Yeah.
Sort of just
Yeah.
shaved a little bit off.
But A, I don't think I'm that good, and B, my machine ain't gonna do it.
This will work.
Yeah.
So this gauge up here, that's how far you're drilling down?
Yeah. Now I actually go past 1 inch because the 7/8 bit has a more of a point to it than a 1/2 inch, you know what I'm saying?
And you're trying to remove material, so.
Yeah.
What kind of material is this that the journals are resting on?
I think it's just like a Delron.
Something that's softer?
It won't hurt the crank, but it's pretty hard. It has to transfer the vibrations.
Oh, okay.
It has to transfer through that material into the sensors in the stands.
Because I suppose if it was soft, it wouldn't be able to do that.
Or it would dampen it, have a dampening effect.
So is this how they make spaghetti?
I think so.
Spaghetti. All gone. So was that the last one?
Oh, these were just the pilot holes.
Oh, these are just the pilot. This is so we're just getting started.
Yeah.
Just getting started. This is the warm up, and now we're going to put the real drill bit in. What drill bit did you just use?
This is a 1/2 inch, and then we're going to go to the 7/8.
Okay. So that's what you meant when you said when you started out with. We start with a smaller bit so that we can get a pilot hole going, and then we go in with the next bit.
It's kind of ugly. Might have to sharpen that.
You got any tools around here to do that with?
I learned how to sharpen bits at an early age.
Would that be with?
My father said, if you're going to be screwing up my drill bits, you're going to learn how to sharpen them. So yeah.
Because I screw up drill bits all the time.
Me and a bench grinder.
And yeah, I was going to say, so many people suggested bench grinder after I used, well, a product that is meant for sharpening drill bits. And I didn't have a whole lot of success with it. And a lot of people were saying, why are you doing that? Why not just use...
Just man up.
Man up and go with the bench grinder.
That's how you learn. You sharpen it and it don't cut. You change it and sharpen it again.
So what you're saying is, as a machinist, you're saying a bench grinder is the way to go.
Yes. This is that radius is kind of hard on. All right, I'm done. We are not fighting that. I'd go to cheat and go on the big belt surfacer.
You're a man of many skills.
Ooh, obviously sharp.
You made it too good.
Holy. I got it off. I'm not centered. Not centered. Well, it's got to go better. It can't get any worse than what it was. It's cutting.
So a slipping belt is better than a broken belt.
Broken bit, yeah. It's getting annoying. I don't want to stop until I got that hole where I want it. So 77 and
83.9.
yeah, so you might as well say 84 times 2 is 168, right? So that still ain't going to be 223, correct?
Sounds like it.
Your mind shut off while you was watching the bit go
I
around.
was completely mesmerized and ready to take a nap. I mean, it was kind of lulling me to sleep, if I'm honest. Because I was like, oh, those gentle sounds of drill bits drilling into forged crank steel. Yes.
Drill bit screaming.
And then the droning of the drill press just being...
So we got it close. We're at 3.3 grams in the front and 1 in the back. And I'd like to get
You've
it a
taken
little
some
closer.
metal out of that crankshaft from what I can see.
A little bit.
I mean, you've got 3 big holes back there, and then you've worked your way in since we last saw you. We basically walked away and let the man do his work because obviously he had a lot of work to do. But how do you know to come into these inner weights?
I didn't want to go any deeper there.
Right.
So I just come in here.
All right, so in other words, you just keep moving in to get the weight?
Well, if I'd have planned ahead and spaced these out farther, this hole would have worked out, but it actually intersected this hole.
And then that was something else entirely.
That's how it goes some days. So now I'm just going to smooth out the burrs. I don't like, your drilling leaves burrs, and I'll smooth them out. I'll smooth a little on the front, and we'll get that 3.3 grams out in the front.
Hence the grinder?
Yeah.
That's what you're doing, you're smoothing up burrs?
Yeah.
So we don't need to worry about the 1 gram in the back, it's 1 gram, right?
Yeah, but it's between me and the machine, and I take it personal now.
Okay.
I will win.
So you're going for the 1 gram then?
That's right.
Yes, sir. Just to let the viewers know, after you're done with all this work, it gets cleaned up before assembled, right?
Yeah.
So it's not like we're going to leave all these metal shavings and everything on here and just throw it inside the block and we're done with it. There's more work to be done. I mean, this work gets done, then it all gets cleaned up and then assembled. So don't be thinking we're just going to throw this in the engine like this. It's not what's happening.
Let's see where we're at.
That might have been your gram right there.
It could have been.
So now we're within 0.2 in the back and 2.4 in the front. .1 in the back.
Yeah, what you do when it gets down to the end, what you do on either end affects the opposite end.
You're not drilling anymore. You're just taking little bits off with the grinder, and that's going to get you where you need to be.
Yeah. I think I'll quit there.
So 0.9 in the front, 0.4 in the back.
Yeah.
That's
Less
outstanding.
than a gram. Yeah.
Less than a gram.
Yep.
So it's balanced now within less than a gram. Awesome sauce.
Thanks.
So the next time you go to the machinist and you're worried about how much balancing costs, he's been here a while. Obviously, as you can see, this started with no holes. Now no offense, but it kind of looks a little bit like Swiss cheese.
I know.
But that being said, this is all in an effort to make a balanced assembly. Once again, I can't stress enough how if you purchase an aftermarket crankshaft, it needs to be balanced unless it is purchased as a balanced assembly. And even so, wouldn't you still want to check your pistons and all that stuff and make sure everything is up to par?
Yeah, I'd still check it. One of the reasons is we went with the SRP pistons, which are lighter than say a lesser expensive or a hyper-eutectic piston. So that's one reason we had to remove as much metal as we did. When they manufacture the crank, they allow for quite a wide variation in bob weights, and we had a pretty light bob weight, so we ended up drilling.
So here we are.
We're our own worst enemy.
I know. Trying to make it better makes it harder to do. Anyway, Kevin, thank you so much for your efforts. Calvinator Engines linked in the description. If you have automotive questions, EricTheCarGuy.com will be linked in the description. Google+, Facebook, Twitter, Instagram. If you wish to connect with me socially, be safe, have fun, stay dirty. Thank you so much for watching. We'll see you next time.